All right, so you want to dive into the world of floating point numbers. Get ready, because we're about to make this surprisingly fascinating.
Absolutely.
You've sent over some really interesting material on this, and honestly, I'm kind of curious too. We're going to break down why these numbers matter, even if you don't dream in code, and hopefully have some aha moments along the way.
It's pretty amazing how they underpin so much of our digital world without most people even realizing it.
Right, like they're the silent workhorses of computers.
Yeah.
So let's start with the basics. What is a floating point number?
Well, according to that 2.8 .pdf excerpt you provided, it's basically a way for computers to represent a huge range of real numbers from, super tiny fractions to astronomically large figures. And the floating part comes in because the decimal can kind of move around, which helps with that massive range.
Okay, so that makes sense. It's kind of like how scientific notation lets us write really big or small numbers without a zillion zeros.
Exactly. Now, something I found pretty interesting in 2.8 .pdf was this emphasis on writing these numbers out in code, what programmers called these like literals with a zero before the decimal point, even for values less than 1, like writing zero point 0.5 instead of just zero point 0.5.
Uh-huh.
It seems nitpicky, but apparently it helps avoid confusion for the computer.
Wow. I did not realize that little detail could matter so much.
Yeah.
I guess it's kind of like how a misplaced comma can totally change the meaning of a sentence.
Precisely. Now, you also included this intriguing flowchart about calculating travel time using floating point number.
Oh, yeah.
Want to dive into that?
Yeah, it caught my eye, too. We've got a trip of 400.5 miles.
And the flowchart breaks down how long it takes to travel that distance by plane and car, assuming the plane's zipping along at 500 miles an hour and the car's cruising at 60.
Okay, so we're using miles traveled, hours to fly, and hours to drive, all floating point variables to make these calculations.
And the beauty of using these floating point numbers here is that they can handle those fractional hours.
Good point. Yeah, we're not dealing with whole numbers in a scenario like this. We might get like zero point 0.8 hours for the flight, right? So it shows how useful floating point numbers are for these like real-world calculations.
Absolutely. And speaking of real-world applications, you even included a snippet of Coral code, which seems to be taking this flowchart and like translating it into actual instructions for a computer.
Yeah, this Coral program's super interesting. I've dabbled in a few programming languages, but never Coral. It's really cool to see how it tackles this problem. We see our same trusty variables, miles traveled, hours to fly, and hours to drive, all set to an initial value of 0.0. What's the deal with that?
So that's actually a common practice in many programming languages. It's kind of like, think of it as the program being extra cautious, like saying, let's just start with a clean slate to prevent any unexpected values from like messing things up.
Huh.
And look at the way Coral handles the calculations.
Oh, wow.
It mirrors that flowchart's logic perfectly.
And the output is exactly the same as the flowchart. I had to say, seeing this flowchart and code side by side is making everything click into place much faster than if I was just reading about floating point numbers in a textbook.
I know. Visuals can be so powerful for understanding these concepts.
Totally.
Yeah.
Speaking of seeing things for myself, I noticed a question that you jotted down on page 4 of 2.8.pdf about assigning the value 7.1 to a variable named package weight.
Mm-hmm.
Were you wondering about the correct way to write that in code?
Well, I'll admit I was overcomplicating things in my head.
In Coral, it's refreshingly straightforward. You simply write package weight equals 7.1.
See, that is way more elegant than what I was picturing. Sometimes it's reassuring how simple things can be.
Right. Now, all this talk about how handy floating point numbers are makes me wonder, are there ever times when they're not the best tool for the job?
Yeah.
I mean, they can't be perfect for everything, right?
You're absolutely right to question that. While incredibly versatile, they do have their quirks and limitations. For example, remember how floating point numbers can represent really big or small numbers using something similar to scientific notation?
Right.
Well, the way they get printed out can sometimes involve some rounding.
Oh, you mean like when that huge number representing the speed of light gets shortened to something like 2.99792E08?
Exactly. And while the computer might still be storing the full precise value in its memory, what we see displayed might be a tiny bit off due to rounding.
So it's like trying to cram a giant complex number onto a tiny Post-it note. You might have to abbreviate a bit. I'm guessing this is where choosing the right type of variable for the task becomes super important.
You hit the nail on the head.
So it's not always best to use floating point numbers.
It depends on what you're doing. Okay.
If you're just counting whole things like the number of people in a room or the number of items in a shopping cart, integers are the way to go. But if you're dealing with measurements or any calculation involving fractions, then floating point numbers are your best bet.
Gotcha. It's about using the right tool for the job. I see we also have some interesting discussions here about using floating point numbers for currency. You even flagged a thread in a programming forum that seemed particularly heated.
Oh, yeah, that one made me chuckle.
Yeah.
There's quite a debate among programmers about using floating point numbers for money because of those potential rounding errors we just talked about. Even the tiniest discrepancy can be a big deal when it comes to finances.
Makes sense. A penny here, a penny there, it adds up. Exactly. That's why many programmers suggest using integers to represent monetary values. For instance, instead of storing $10.50 as a floating point number, you'd store it as 10 and 50 cents as an integer. Avoids those fractional headaches entirely.
That's a really clever workaround. Okay, I have to ask about this. Dividing by zero. It's like the ultimate mathematical taboo. What happens in Coral if you try to divide a floating point number by zero? Do you create a digital black hole?
Don't worry, no black holes here. But it's a great question, and it highlights how different programming languages handle things. Coral, instead of crashing, gives you a specific output. Infinity.
Whoa, infinity. Like the actual concept of infinity.
Yep. It's Coral's way of saying, hey, this result is too large to represent in a normal way.
That's kind of cool.
Yeah.
But also potentially problematic, right? Like, what if you're building software that controls something important and suddenly you get an infinity error?
You're thinking like a programmer already, and that's precisely why understanding these potential errors and how to prevent them is so important in software development. We don't want our code throwing infinity tantrums when we least expect it.
Definitely not. Especially if it's controlling a self-driving car or something.
Exactly. Now, it's worth noting that other programming languages might have slightly different ways of dealing with dividing by zero. Some might give you infinity, others might give you not a number, often shortened to nan.
So it's like different languages having different words for the same thing.
Precisely. They're all expressing that same underlying idea in slightly different ways.
It's like they all have different ways of saying, whoa, you can't do that.
Yeah.
But really, it's amazing how much we've uncovered about floating point numbers already. They really are essential to modern computing, aren't they?
Absolutely. They're kind of the unsung heroes powering so much of the technology we rely on.
Okay, so if we had to boil all this down to the top 3 things our listeners should remember about floating point numbers, what would they be? You know, the need-to-know stuff.
Okay, love it. Here's the highlight reel.
Yeah.
So first, floating point numbers are champions at representing a huge spectrum of values. They're used everywhere from scientific simulations that model the universe to the video games we escape into.
Right.
They're what let computers deal with the messy, often fractional numbers we find in the real world.
Yeah.
Second, rounding errors. We touched on this earlier, but it's worth emphasizing. Even though these errors are often tiny, they can snowball, especially in things like scientific research or financial models where precision is paramount.
It's a great reminder that computers aren't perfect. I mean, they're amazing, but they do have their limitations. What's that third takeaway?
Third takeaway is a big one. Choosing the right tool for the job. Floating point numbers are versatile, but they're not always the best choice. Sometimes using integers or other data types is a smarter move and will save you headaches down the road.
Right, like we talked about with representing currency. Now, you mentioned those rounding errors, and it made me think, are there times when you actually want to round a number? Like if you're displaying a price to a user, you probably don't need to show them 5 digits after the decimal point.
Excellent point. There are definitely times when you want to control how numbers are rounded, especially for display purposes. Luckily, most programming languages have built-in functions for this. You can tell the computer exactly how you want the number rounded, making sure it's both accurate and user-friendly.
It's like choosing the right level of detail for a map. You don't always need to see every single tree. Sometimes a zoomed-out view is more helpful.
That's a great analogy. And it kind of speaks to the broader theme of balancing precision with practicality, which is a key consideration when working with floating point numbers.
It makes you realize how much thought goes into designing even the simplest seeming features of software. It's not just about making things work, it's about making them work well for the people using them.
Absolutely.
Yeah.
Now let's circle back to that mind-bending concept of infinity and how some programming languages like Coral handle dividing by zero. It's like peering into the realm of the infinite, but within our digital machines.
Right. It seems like such a paradox. Infinity is this vast, unimaginable concept. Yet here we are representing it with a few bits of data. It's wild.
It really speaks to the incredible power of abstraction in computer science. We can take these complex, sometimes mind-boggling concepts and encapsulate them in a way that allows us to work with them, to reason about them.
Which then allows us to do incredible things like simulate the birth of stars, predict the weather, or even have this very conversation.
Precisely. It's a testament to human ingenuity and our drive to understand the universe, even its most mind-boggling aspects.
Speaking of mind-boggling, are there any real-world situations where dividing by zero or encountering infinity actually makes sense? I have to admit, my brain is starting to hurt a little just thinking about it.
That's a fantastic question, and it might surprise you to learn that there are. It's not that we're literally splitting something into zero parts, but in certain branches of mathematics and physics, like calculus, these concepts are useful tools for analysis and modeling.
So it's more of a theoretical tool in those cases.
Exactly. It's like those spherical cows in a vacuum physics problems you might remember from school, a simplified way to understand complex principles.
Ah, right. We're not launching any cows into space. But those thought experiments help us grasp the fundamentals.
Exactly. And speaking of fundamentals, I think it's worth revisiting the importance of choosing the right data type, something that often trips up new programmers. Integers and floating point numbers are essential, but they're just the tip of the iceberg.
Right. There are also things like characters, strings, booleans. It can feel a bit overwhelming, like walking into a well-stocked library and not knowing where to start.
It's all about understanding that each data type has its strengths and weaknesses, just like tools in a toolbox. You wouldn't use a hammer to tighten a screw.
Exactly.
And you wouldn't store a password as a floating point number or try to represent a complex image using only integers.
Why?
It all comes down to understanding the strengths and limitations of each data type and then making strategic decisions based on what you're trying to accomplish.
Right. So it all comes down to understanding the strengths and limitations of each data type, and then making strategic decisions based on what you're trying to accomplish.
Precisely. And this highlights the critical role of careful planning in programming. Before writing any code, it's crucial to think about the kind of data you'll be working with, how it needs to be stored, manipulated, and displayed, and what data types are the best fit for those tasks.
It's like designing a building. You wouldn't just start piling bricks on top of each other without a blueprint. A solid foundation is essential.
A perfect analogy. In programming, that foundation is a well-thought-out data model. It's a key principle for creating reliable and maintainable software.
So planning is paramount. Which makes sense, but it's easy to get caught up in the excitement of coding and forget about the planning stages. Now, I'm curious. We've talked a lot about how floating point numbers are represented, but what about how the computer actually does math with them? Is it significantly different than how we do math with pen and paper?
Another good question. And the short answer is, yes, there are some key differences. Remember that computers store everything, including numbers, in binary form as sequences of zeros and ones. And just like we have rules for performing arithmetic in our decimal system, computers have algorithms for doing the same in binary.
Okay, that makes sense, but I imagine working with fractions and decimals and binary gets a bit messy.
It can. And that's where floating point representation comes in. It's similar to scientific notation, but in base 2. We have a sign, positive or negative, a significand, the essential digits of the number, and an exponent, a power of 2, all represented in binary.
So it's like the speed of light example we talked about earlier, but in the language of computers.
Precisely. To perform calculations, the computer breaks down each floating point operation into a series of simpler operations on the significand and exponent, all done in binary. It's like the computer has its own special set of binary math tricks.
It's amazing how much complexity is hidden beneath the surface of what we see on our screens. It's like those elegant mathematical proofs that seem almost magical, but are built on a foundation of logic and reasoning.
What a brilliant comparison. It highlights the incredible ingenuity behind these systems.
Okay, confession time. Whenever I hear floating point, I can't help but picture these numbers literally floating around inside the computer. It's probably not the most accurate mental image.
No, I kind of love that. It's not that the numbers themselves are physically floating, but it's a good way to think about how flexible their representation is. Remember, floating refers to the fact that the decimal point can move around depending on the number's size.
Right, so it's less about the numbers themselves floating and more about how their representation can adapt, making them incredibly versatile.
You got it.
You mentioned earlier that different programming languages might handle floating point numbers a bit differently. Are there any languages known for doing it exceptionally well? Or, on the flip side, any that are notoriously tricky?
I'm glad you asked. Fortran, a language often used in scientific and engineering computing, has a long-standing reputation for its floating point performance and accuracy.
So if you're doing serious number crunching, Fortran is your go-to.
It's definitely a top contender. On the other hand, some languages prioritize ease of use and rapid development. They might make certain trade-offs in their floating point implementations, which could lead to a slightly less accurate or less predictable results.
So it's that classic balance between convenience and precision again.
Exactly. Choosing the best language often comes down to the project's specific needs. If you need extreme precision, like for a high-performance simulation, you'd prioritize a language known for its numerical rigor. But if you're building a web app where small discrepancies in calculations won't make a huge difference, you might choose a language that emphasizes developer productivity. It's all about finding the right tool for the task at hand.
As always, I don't want our listener to think floating point numbers are something to be afraid of.
Not at all. They're powerful tools.
What advice would you give to someone feeling a bit overwhelmed by all the nuances we've discussed?
Approach it with a mix of curiosity and caution. Don't be afraid to experiment and play around with how these numbers work, but always remember those potential rounding errors. When in doubt, consult the documentation for your chosen programming language. Experimentation and documentation. Every programmer's best friends.
I love it. And, it strikes me that there's something quite profound about all of this. I'm reminded of that quote by Lord Kelvin, "To measure is to know."
Ooh, that's a good one. It perfectly captures the importance of measurement and how crucial floating point numbers are to our understanding of the universe.
Without them, our understanding of the world would be so much more limited.
They're the unsung heroes behind countless scientific breakthroughs, technological marvels, and even everyday conveniences.
It's true. From the smartphones we use to the rockets we launch into space, floating point numbers are quietly working their magic.
They're the silent partners in our pursuit of knowledge and progress.
So next time you're using your favorite app, playing a video game, or learning about some amazing new scientific discovery, take a moment to appreciate the humble floating point number. They might not always get the spotlight, but they're the workhorses that make so much of what we take for granted possible.
Yeah, here.
I'm starting to see them as the unsung heroes of computing. Not always glamorous, but absolutely essential.
They're the foundation upon which we've built the digital age.
Speaking of foundations, I think it's time to start wrapping up this deep dive. We've covered so much ground.
It's been quite the journey.
Before we sign off, any final thoughts for our listener? What's one key takeaway, one nugget of wisdom you hope they'll carry with them from our exploration into the world of floating point numbers?
That's a great question. If I had to choose just one thing, it would be to approach floating point numbers with both respect and wonder. Respect for their power and precision, and wonder at the ingenuity that allows us to represent and manipulate such a vast range of values within our digital machines.
Beautifully said. It's a great reminder that even in the seemingly small details of computer science, there's always more to learn, more to appreciate, and more to spark our curiosity.
And who knows what new discoveries await us as we continue to explore the possibilities of these fundamental building blocks.
It's funny, we've talked about dividing by zero those sneaky rounding errors and the importance of picking the right data type, but it makes you wonder, are there times when programmers actually want to bend those rules a little? Like, is there a method to the madness?
Oh, you're getting into like the realm of creative coding. It reminds me of how musicians sometimes embrace those imperfections of analog equipment to create like unique sounds.
Exactly. Think about those like mind-blowing special effects in movies, or the way video games create these incredibly detailed worlds, or even those mesmerizing digital art pieces you see online. Sometimes it's those unexpected results, those moments where the computer seems to break from strict logic that leads to something truly innovative and beautiful.
Yeah, it's like those happy accidents in the lab that lead to groundbreaking discoveries.
I love that. So to our listener, I leave you with this challenge. Don't be afraid to experiment, to push the boundaries of what you think you know about floating point numbers. Who knows what you might discover?
That's the beauty of coding. The journey of exploration is just as rewarding as the destination.
Absolutely. And on that note of exploration and pushing boundaries, we'll wrap up our deep dive into the fascinating world of floating point numbers. We hope you've enjoyed the journey as much as we have.
Until next time, happy coding.
And remember, in the world of tech, there's always something new to learn. This is The Deep Dive, signing off.